Welcome to our presentation for ELEC 445, Design of MEMS and Flexible Sensors for Wearable Devices. In this presentation, we will briefly describe our technical properties and background information of the device, which is a MEMS Michelson interferometer. Then we will talk about our simulation and its results, and then finish the presentation with a brief conclusion. This is the outline of the presentation. We agreed on to work on a MEMS Michelson interferometer, which is a device used to measure the wavelength of the light. In this figure on the left, you can see the basic outline of the device where two mirrors, one of which is movable, used with a beam splitter and a light source. When the light coming from the light source reaches to the beam splitter, it is split into two beams that travels to the mirrors whose normals are perpendicular. Then reflected beams come to a splitter to be directed to a plane or a detector. On the plane or detector, an interference pattern of light can be observed due to light's wave-like nature. This pattern changes as the movable mirror adjusted, causing constructive and destructive interference patterns at the center, as seen from the right figure. Next figure explains the phenomena. Assuming the mirrors were equidistant from the beam splitter at the beginning, if the mirror moved a quarter of the wavelength, its phase shifts by pi, causing a destructive interference at the center. If the mirror move half of the wavelength, its phase shifts by 2 pi, which produces a constructive interference at the center. By adjusting the mirror, this process can be observed repetitively and interference fringes can be counted. Using number of interference fringes, which is m, we can calculate the wavelength of the light by the formula delta d equals m times lambda over 2, where delta d is the displacement of the mirror.
Thank you. Now I will continue with the theory and working principle of the device. This device can be modeled as in the figure of the left basically. It consists of two parallel plates, a spring and a damper. This is the model for the device. Right image presents the circuit equivalent of the device in mechanical and electrical domain. This device is basically a transducer that converts electrical energy stored in the electric field to mechanical energy as an actuator. This slide and the next one show the equations used to model the device. Here, K variable in the first equation is the spring constant. Now, I should briefly mention the pull-in effect. Right figure shows the behavior of such a device. As the voltage difference between plates increases, plates come closer and the mechanical force balances this with the spring and damper. When the voltage difference reaches to a certain point, the mechanical forces is no longer able to balance the system and the system collapses. Two plates stick to each other, and this behavior is observed in the figure as well. In order to prevent short-circuiting two plates, we placed an insulator between plates as seen in the right figure. This graph is taken from the paper by Nemirovsky. In their paper, Nemirovsky et al. Stated that pull-in occurs when first and second derivative of total energy of the system with respect to displacement is equal to 0. Here, the total energy is calculated by summing the mechanical and electrical energy of the system. Using this formula, we can calculate the pull-in effect. Let's move on the design specifications. This is our design for the device. And this page includes design specifications of the device, which we used in the simulation. We also included these parameters in the report.
All right, thank you. Let's move on to simulation results. The displacement versus voltage and time graphs are displayed in this slide. When we look at the right graph, we can see that the blue trajectory is the forward voltage actuation, which is increasing the voltage, and the red one is the backward voltage actuation, which is decreasing it. And on the left side, we can see how the displacement and voltage changes via time. This is the time response of our system for different voltages. As you can see, pull-in effect has a dramatic influence on the system even though the voltage is changed slightly from 9.30 to 9.34 voltage. And for higher voltages, the pull-in effect occurs. Now I will mention the effects of scaling on the device. On this page, you can see the effect of increasing and decreasing different parameters on pull-in behavior. As the mass of the mirror decreases, the pull-in voltage and distance decreases too. Increasing the mass, on the other hand, increases these variables. And the mass is not the only factor that changes pull-in voltage. Also, the Q factor changes. And when we decrease the Q factor, the pull-in voltage and distance increases and vice versa, which is the opposite effect of the mass. Now we can see the displacement graph for different voltages for our scaled system, where the width and length are scaled by the factor 10 to the 3 and the thickness and gap between plates are scaled by the factor 10. As it can be seen from the graph, the pull-in voltage is decreased to 2.46 and the displacement is 5 times smaller before the scaling. While reducing the size of the capacitor, we do not want to lose stiffness, and it can be achieved using appropriate scaled factors. Since we reduce the length of the capacitor, it will increase the stiffness even though width and thicknesses are reduced, because we use the different and appropriate scaling factors for these parameters. We can see from the table that by reducing the size, pull-in voltage is reduced. However, spring constant is reduced as well, which is an undesirable outcome. And it is because we first used the same scaling factor, which is 10 for all parameters, and then we made further experiments and increased the spring constant by increasing thickness, but this time pull-in voltage is increased as well. The successful scaling for these factors are shown in the previous slide. In this slide, we can see the other important parameters. For example, the frequency, which is increased by the scaling down our system, and also the consumed energy and switching time, which are one of the most important factor parameters are reduced too. And this is the end of our presentation. Thank you for listening.